In this video, we're going to talk about suggested homework problems from 10.6. We'll be talking about polar equations of conics. This will be our last video for our Calculus 2 topics. We will not be talking about Kepler's law specifically, but I'll make some comments at the end about how these types of equations refer to the things that Kepler was looking at and how the reason he derived these things in this form and how we have learned these apply to all these shapes outside of what he was studying with planetary motion and motion of celestial objects, let's say. So before we get started with number one, we're looking at polar form of conics are going to be in the form of eccentricity times, and if you remember, we had the distance between the focus and the directrix was called P in pre-calculus. I'll call it that again, and this is going to be 1 plus or minus E cosine theta, and R is equal to EP over 1 plus or minus E sine theta. So if we see cosine theta in the problem, we know that the action is happening in the horizontal direction because cosine is related to x. So we have a axis of symmetry for a parabola that's horizontal and it's going to open left or right, or a transverse axis for a hyperbola that's in the horizontal direction parallel to the x-axis and it's going to open left to right, or a major axis for an ellipse that is in the horizontal direction parallel to the x-axis and it's going to be stretched out in the x direction. I think that's everything. If I have sine, it's like that, but in the y direction, so axis of symmetry or transverse axis or major axis in the y direction. So let's go ahead and let's look at number one, and we'll use this coefficient in front of sine or cosine to help us find the eccentricity. Once we have made sure that this number that's in the front here without the sine or cosine is 1, we won't worry about the numbers up top right now. We would worry about those if we were trying to change things back into rectangular form, which we're not going to do. We'll just use the calculator to graph when we need to do that later. So R is equal to 4 over 1 plus 3 sine of theta. So my R is equal to 3. You didn't say this before, but maybe you remember this from pre-calculus. If my eccentricity is between 0 and 1, I have an ellipse. If my eccentricity is equal to 1, I have a parabola. If my eccentricity is greater than 1, I have a hyperbola. You may or may not have talked about eccentricity in your pre-calculus class. It's fine if you didn't. You'll discuss it a little bit here. So this is greater than 1, so I have a hyperbola. And what this tells me is that the directrix to this focus that I have is above my focus, which the focus that I'm looking at when it's in polar form is always at the pole at 0, 0, the origin, since we're kind of going to be looking at this in XY, even though it's given to us in polar. I'm not really going to graph it with polar coordinates. I'm going to make XY. Actually, I'm just classifying this, so I really don't need to graph this. We'll graph some more later. So, but if you wanted to graph this, you would think about what goes in the vertical direction. So that would be pi over 2 and 3 pi over 2. You would use those to find your vertices, because they would be those distances that were on that axis. And then you would find some additional points, probably your x-intercepts, by looking at 0 and pi, and use symmetry to help you get the same points on the other piece. And you may even be able to find your center and have those points kind of help you box in the region that is not covered by the hyperbola, and that you can draw corner to corner of the asymptotes and see what it approaches. So all that was in your pre-calculus textbook as well. So r here is equal to 1. This is a parabola. Just classifying these. If r is equal to 8 over 6 plus 5 sine of theta, then I need to divide by 6. That's going to be 4/3 over 1 plus 5, 6 sine of theta. E is equal to 5, 6, which is less than 1, so I have an ellipse. And then D is r equals 3 over 2 minus 3 sine of theta. I'll pull this down. So that's 3/2 over 1 minus 3/2 sine theta. E is equal to 3 over 2, which is greater than 1. So I have a hyperbola. Let's look now at problems 7 through 12. And we'll not only classify these, but we'll match them with some graphs. So 7 says r is equal to 6 over 1 minus cosine of theta. So this is E is equal to 1. And so it's a parabola. It's a parabola with the directrix to the left of the focus. And since we open away from the directrix, this is going to open right. So let's look for a parabola that's opening to the right. That's C. There's no other parabola that's opening to the right there. Let's look at 8. R equals 2 over 2 minus cosine of theta. So this is equal to 1 over 1 minus 1/2 cosine of theta. E is equal to 1/2. So I have a ellipse. And this ellipse has cosine in it. So it has a major axis that's on the x-axis here. So let's go ahead and look for an ellipse that is a major axis on the x-axis, and that is F, 9. If I put in the focus on 0, 0, we ensure that our major axis or our transverse axis is always going to be the x-axis or the y-axis, because those axes are going to go through the foci. So let's go ahead and look at r equals to 3 over 1 minus 2 sine theta. So E is equal to 2. This is a hyperbola. Transverse axis is the y-axis here. So let's look for a hyperbola with the transverse axis being the y-axis. That's A. 10. R equals 2 over 1 plus sine theta, we have E is equal to 1. So we have a parabola, and this parabola has a directrix that's above the focus, so it's going to open down. So let's look for a parabola that opens down. That's E. And then 11. Have R is equal to 6 over 2 minus sine theta. That's 3 over 1 minus 1/2 sine theta. Our E is equal to 1/2. So this is an ellipse, and this ellipse has a major axis along the y-axis. So let's look for an ellipse, major axis along the y-axis, that's B. And then number 12, R is equal to 2 over 2 plus 3 cosine of theta will be 1 over 1 plus 3/2 cosine of theta. So E is equal to 3/2, and that's greater than 1. So we have a hyperbola with a transverse axis along the x-axis here. It's going to open left and right. So that's going to be D. So far, we haven't had to graph anything, but we're going to do that now, starting with number 13. Thirteen gives us R is equal to 1 over 1 minus cosine of theta, and our E is equal to 1, so I know I have a parabola, and I know that this parabola opens right because it has a directrix to the left of the focus here. But I need to get that vertex that's going to lie on the x-axis here. So I need to get theta is pi, because that's going to make me look to the left. And R is going to be, let's see, 1/2. So there's my vertex there. And I'll get some points that are going to lie on the y-axis. There's not going to be any other point over here to the right on the x-axis because it opens to the right. So I won't cross the x-axis again. But we can look at pi over 2, and that'll be 1 over 1 is 1. And 3 pi over 2 will also be 1 over 1 is 1. And my parabola opens to the right here. I'm going to go ahead and let my calculator graph that as well. So I have 1 divided by parentheses 1 minus cosine theta, close parentheses for the denominator, zoom 6, and you can see that parabola with a vertex at negative 1/2 0, opening to the right there. It passes through 0, 1, and 0, negative 1. Let's go ahead and look at number 15. R is equal to 7 over 4 plus 8 sine of theta. So I want to make this 7/4 over 1 plus 2 sine of theta. My eccentricity is 2, which gives me a hyperbola. And the action is going on in the vertical direction here. I have a transverse axis along the y-axis. So let's go ahead and look at theta and R, and I'm interested in those vertices that are going to happen at pi over 2 and 3 pi over 2 since I'm on the y-axis. Sine of pi over 2 is 1, so that'll be 7 over 12, and 3 pi over 2 gives me negative 1, so that's going to be negative 7/4. Won't hurt me to find my x-intercept, so let's go ahead and find those at 0, 7/4, and Then we have at pi, that'll also be 0 and 7/4. So those are some kind of funky numbers there, but let me see what I can do. So if I can make my tick marks 7/12, then let's see, 7/6, and then 7/4, negative 7/12, negative 7/6, negative 7/4, 7/12, 7/6, 7/4. So let's go ahead and look here at what's going on. I'm not going to get a complete picture of this, but at pi over 2, I go to 7/12 when I'm looking that way. When I'm looking 3 pi over 2, I go negative 7/4. So all the way up here, that's my other vertex at the other end. And then we have x-intercepts at 0, 7/4. And when I'm looking in the direction of pi, I also walk 7/4. So that's negative 7/4. And I have some symmetry here. So if I am, this is the center, it's halfway in between here. So when I go another tick mark here, this is also here and here. And so we get these asymptotes that are going to box this in, kind of go like this. And let me try and draw these a little better to go through this point, to go like this and like this. We're going to get closer to the asymptotes as we go out to the ends here. Get closer to the asymptotes out at the ends here. And the calculator is going to do a way better job at drawing a hyperbola than I do. So let me go ahead and let the calculator draw this for you. So it's 7 divided by 4 plus 8 sine theta. 6. There it is. You're even going to see those asymptotes that I was trying to sketch. It's actually going to draw them, and it's going to show the two pieces there with the y-intercepts at 7/12 and 7/4, and the x-intercepts will be there at plus or minus 7/4. All right, let's look at number 17. R is equal to 6 over negative 2 plus 3 cosine of theta. This is a negative 3 over 1 minus 3/2 cosine of theta. And we have our E is equal to 3/2, which is greater than 1. So we have a hyperbola, and our hyperbola has a transverse axis, that's the x-axis here. So we're going to be opening left and right with our hyperbola. And let's look then at theta values of 0 and pi. And this is going to be 6 over negative 1 is going to be negative 6. And I'm sorry, yeah, that's right. And then 6 over -5 is -6/5 or -1.2. So this is, what did I say, -1? That's 6 over 1. That's 6. Cosine of 0 is 1. 3 times 1 is 3. 3 minus 2 is 1. 6 divided by 1 is 6. So when I am looking in this direction, 1, 2, 3, 4, 5, 6. There we go. And then when I'm looking in the other direction, walk 1.2 backwards. And that gives me my other endpoint of my other vertex here. Excuse me. And my center is halfway in between. So 6 plus 1.2 divided by 2 is 7.2 divided by 2 is 3.6. So 3.6, my center is right there somewhere. And let's look at some other points that are going to be on my y-intercepts here. So that's going to be -3. This is also going to be -3. It's 1, 2, 3, and 1, 2, 3. And so when I go 1.2 to the right of this one, I'm also at 3 and -3. And my hyperbola is opening to the right here. I have some asymptotes that are going to box this in. Let's go ahead and let my calculator draw this for me. Again, that's just a sketch. Calculator is going to get it really good. So -2 plus 3 cosine of theta, zoom 6, and you can see that that opens left and right with x-intercepts at 1.2 and 6, and y-intercepts at -3 and 3. Additional points over here at 7.23 and 7.2, -3. Let's look at number 19. R equals to 6 over 2 plus cosine of theta. So this is 3 over 1 plus 1/2 cosine of theta. This is going to be an ellipse because my E is equal to 1/2. And this opens left and right. So I'm interested in the endpoints where theta is 0 and pi. So 6 over 3 is 2. 6 over 1 is 6. Two and pi over 2 and 3 pi over 2 is going to give me 6 over 2 is 3 and 3. 1, 2, 3. 1, 2, 3. And do my best here to draw this. And the center is 6 plus 2 is 4. So 1, 2, 3, 4. The center is here on this line. That's something like that. So this is 6, let's clear out this, 6 divided by 2 plus cosine of theta, zoom 6, and there it is. And let's look at number 21. R is equal to 300 over negative 12 plus 6 sine of theta. And this is just not going to be nice to graph because of these big numbers. If I divide by negative 12, this is going to be negative 25 over 1 minus 1/2 sine theta. So my E is equal to 1/2. I have an ellipse, and its major axis is in the y direction along the y-axis. So let's go ahead and look for those endpoints that are at pi over 2 and 3 pi over 2. This is going to be kind of funky because they both come out to be negative numbers because of this. So 300 divided by negative 6 is negative 50. And then 300 divided by negative 18 is negative 16 and 2/3. Let's look at what happens at 0 and pi as well. 300 divided by negative 12 is negative 25 for both of these. So I think I'm going to choose tick marks to be 5s here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see, 1, 2, 3, and this number divided by 5 is negative 3 1/3. So 2, 3 1/3 is right there. So that number minus 50 times negative 1 divide by 2. And then that's divide by 5 to see how many tick marks to go. I need to go 6 2/3 to get to the center. 1, 2, 3, 4, 5, 6, and 2/3. There's my center. And so I have a center line that is out here somewhere. And I have, let's see, 1, 2, 3 1/3. 1, 2, 3 1/3 should get me over here and over here. Okay. So this is really crazy looking, but it's not really doing a great job with this, sorry. I want my calculator to do a much better job with this. Kind of like that. Still stretched out mostly in the y direction, but 300 divided by -12 plus 6 sine of theta, and try and graph that. We're not going to see anything. Zoom 0, and then I'll zoom square to square this up and give it the right shape. And there it is. All right, that's it. I promised you also at the end of this that I was going to talk about why we care about polar forms of these equations. It mostly has to do with the movement of planetary objects is how this started. You can read about Kepler's laws in books that asteroids, comets, planets, things like that will travel these types of paths. You probably know that planetary motion follows elliptical paths with the sun at one of the foci. There will be some problems in the book where you find that, and let's say that this was the path right here, that one of the ends of the major axis here that was closer to this focus with the sun would be the closest that the planet gets to the sun, and that's important. And then this other end of the major axis here would be the furthest that the planet gets away from the sun, and that would be important. Those have some special names, and you'll want to find those for some of those problems that are in the book, or maybe that you're going to get assigned for homework. The more eccentric that the path is, the more elongated this is, the less circular it is. The closer the eccentricity is to 0, the more circular the orbit is. Let's see what else. Some things like comets that are on these elliptical paths like this, like Halley's Comet, will come back through our solar system every so often. But if they don't, if they're on parabolic or hyperbolic paths instead, they'll only come through one time. So you'll hear things on the news sometimes of things like, you won't see this again for another 50 years or something like that. Well, that tells you that it's elliptical and that it's going to be coming back. And sometimes you get these things that say, this is the only time you're ever going to get a chance to see this. Don't miss this. It's on some kind of parabolic or hyperbolic path through our solar system. And if you miss it, it's never coming back this way again. So Kepler was interested in those types of things, but we figured out that what he was studying in the big scale for the universe and the way in which these celestial bodies moved and things like that, that it could be applied to many other things here with conic sections. We already had some idea of those things with rectangular coordinate system as well, that Descartes was studying a lot of those things, putting them in terms of X and Y, but Kepler really did the work to put these in terms of R and theta, and giving us this other way to talk about things in terms of the distance from the from this pole, which is going to be one of the foci, which again, he always put the sun there. The distance away from the sun changing as a in relationship to this angle here, this central angle. And I already mentioned that by putting the focus there at the pole, you ensured that either your x-axis or your y-axis was going to be your axis of symmetry, your transverse axis, or your major axis. So, all right. That's it for everything for this video. That's it for Calculus 2. And from here, you can go on to Calculus 3, linear algebra, or differential equations. So be on the lookout for those videos. Some of those exist already at the time that I'm making this, some of them don't, but hopefully I get sets of videos up for all of those classes in the near future, if I don't have them complete already. So good luck with your next math class that you're taking after this, or if you're done with your math classes now, congratulations. I know some of you finish after Calculus 2, and good luck with whatever you're doing next. So see you next time if you're coming back for another math class.